Hello and welcome to Design Deep Dive. In this first episode, we take a look at some of the more interesting and unusual features of the Saab 340, original turboprop that started life in the 80s. I will say lots of words about it shortly, but first I'll just let you immerse yourself in the sights and sounds of one of the nicest 340s around as we begin our final approach into a sunny Southampton airport. So let's take a design deep dive into this rather fetching Swede behind me. Actually a Swedish American as what we know today as the Saab 340 started life as the SF340, a joint project between Saab and Fairchild Aircraft to develop a new 30-ish seat Part 25 turboprop. In the mid-80s, Fairchild withdrew from the project, and subsequent examples of the aircraft became known as the Saab 340A, up to the 159th airframe. Following an engine upgrade, at that point the next couple of hundred airframes were designated as 340B. Finally, after adding active noise cancellation, cabin improvements and a gravel runway capability, the final model would be named 340B Plus, which took us up to a total of 459 airframes built. Now, this particular B Plus, Golf November Foxtrot Lima Bravo, is a rather special one. It serves as a specially instrumented flying laboratory for the National Flying Laboratory Center, more on which presently. It is one of the youngest around, one of the last 5 ever built in 1998. It served in the US for Mesaba Airlines, first in Northwest Airlink colors, then in a Delta Connection livery after the Northwest Delta merger. When Mesaba ceased operations in 2011, it was stored in Bangor, Maine, then transferred back to Saab in 2014. Its new life with the NFLC began in 2021, when it underwent an extensive refit. Mesaba had flown it in a one-class 34-seat configuration, which was retained, except for one seat in the back row, which was removed to allow access on the ground only to the cargo hold. Now, you would expect a few quirks on a Saab, and the tail delivers. First, the fin is quite large, as you'd expect on a relatively short twin turboprop, and it has a long triangular dorsal extension with a flat profile. It's there to prevent side slip developing to the point where the rudder might become ineffective. It does this by generating quite a bit of vortex lift at high side slip angles. There's also a pair of ventral fins. Now, there could be a couple of reasons for these. Most probably, these ones are there to improve the natural Dutch roll damping of the aircraft. By the way, on the airborne early warning version of the 340, which has a large radar in front of the main fin, these were enlarged to enormous sizes. Another interesting quirk of the tail is this little triangular fin, which is just forward of the leading edge of the tailplane, presumably also there to generate a vortex which improves the effectiveness of the tail, keeping the flow attached at high alpha. The other interesting feature here is the huge dihedral angle on the horizontal stabilizer, if you can still call it horizontal. About twice that of the wing, 15 degrees, most likely an attempt to keep most of the tailplane out of the prop wash. Now, this much stabilizer dihedral isn't unprecedented, especially on shorter turboprops. Witness the Vickers Viscount also coming in at 15 degrees. You can see it on high-wing aircraft as well, such as this Rockwell Commander, where the downwash effect of the main wing might also become a more significant factor in all this, especially at high alphas. Though lest we rush into generalizations, here's a very similar but conspicuously flat tailplane Twin Otter. Sometimes tailplane dihedral is also used, as we feast our eyes on the Viscount once more, as a relatively inexpensive means of tweaking the lateral stability of the aeroplane. Perhaps the primary motive behind what Vickers did here, as well as later on the much larger Vanguard. You can just about make out its angled tailplane behind all that scaffolding. In any case, back to the Saab. Another quirk, there is a row of vortex generators on the underside of the tailplane. Here. but only on the right-hand side, suggesting that this too has something to do with prop wash. Note that both props turn clockwise when viewed from the tail. Related also, the yaw trim is set to 1.5 degrees for takeoff. The propellers rotating in the same direction means that you can have two mostly identical powertrains, and this is a feature common to many multi-engine turboprops. Essentially, it means that you don't need specific left-handed and right-handed parts. But ironically, this comes with a variety of awkward aerodynamic asymmetries. Because the descending blades on both sides see slightly higher angles of attack, especially at higher aircraft alphas, the thrust lines of the two engines are offset to the right. Which means that the thrust vectors don't go through the spinners. They are offset. What this means is that the yawing moment of the thrust of the right-hand engine will be greater than the yawing moment of the thrust of the left-hand engine. And that's simply by virtue of the longer moment arm on the right-hand side than on the left-hand side. Additionally, the prop wash of the right-hand engine will enhance the lift generated by the wing a little bit further outboard than on the left-hand side, which means that you will also have a slight rolling moment to the left as a result of this asymmetry. What all this means is that the left engine is the critical one. Losing it is the worst contingency against which you have to design every feature of the aeroplane related to the one engine inoperative lateral directional stability, and in fact even the one engine inoperative pitch stability of the aeroplane. And we have seen some of these features already, the large fin as well as the preemptive rudder trim set to the right. But the quirkiest of all of these features, and perhaps the most unusual feature of the entire aeroplane, and this actually warrants a change in pen color at this point, is that both engines, and thus their thrust vectors, are set to point to the right of the center line by 3 or 4 degrees. The forward sections of the nacelles actually curve to the right as well. If you're facing the aeroplane, the prop discs are not facing you, they're actually looking slightly to the right. Now, I do not wish to claim that I know Saab's exact design rationale behind this, but this oblique setup does a number of things. It evens out the one engine inoperative yawing moment somewhat. I draw the actual thrust lines. I'm obviously really exaggerating this. We're only talking 3 or 4 degrees out. What I've drawn here is more like 40 in the interest of making the geometry easier to see. Because we are reducing the moment arm on the right. I suppose we're increasing it slightly on the left. What it also does is it turns the slipstream of the right-hand engine slightly into the tail, specifically into the fin, increasing the restoring moment on it in case of the loss of the critical engine. Incidentally, what might also happen at high alphas, perhaps combined with high yaw angles, is that the slipstream of the right-hand engine locally increases the alpha at the root of the tailplane, hence the need for that row of vortex generators we saw earlier. Now, speaking of high yaw angles, maintaining rudder authority at large deflections is rather important, which would explain the large number of rudder leading edge vortex generators on the Saab, and indeed on other twin turboprops, very prominent on this Airbus C295. Let's talk about the engines. We have two GE CT7-9B turboprops developing a maximum takeoff power of 1,870 brake horsepower on the propeller shaft. This is flat rated such that you get that power regardless of conditions up to 35 Celsius ambient temperature. Now, down the tailpipe we get a bit of additional jet thrust, 743 newtons to be specific, in takeoff conditions, about the weight of an average adult. You would need about 65 horsepower on the shaft to generate that with the propeller, so the total equivalent power on takeoff is about 1,935 equivalent shaft horsepower. To put this in automotive terms, this one engine produces the power of about 30 entry-level Ford Fiestas or VW ups. 29 on the shaft, 1 through the jet pipe. Now, of course, you then lose quite a few of those on the prop, as it is not as efficient as a wheel is at turning power into locomotion. Then again, you can't climb to 25,000 feet in a Ford Fiesta, so there's that. Another interesting feature of the CT7-9B is that it has a free-running power turbine at the back here, which is only connected mechanically to the gearbox at the front, which drives the propeller. It's not connected to the gas generator or the turbine that drives the gas generator. This means that if you apply the brake to the propeller, you could run the gas generator and its turbine on their own. So you could use that as an APU, for example. And indeed, such a brake was fitted as an optional extra to some Saab 340Bs. Speaking of the prop, the 4 magnificent composite Doughty rotor blades turn once every 15.9 revolutions of the power turbine, courtesy of the gearbox. So, for example, when the constant speed governor sets the propeller RPM at 1,396 for takeoff, the power turbine is spinning in excess of 22,000 RPM. At this point, the combustion gas temperature exceeds 900 Celsius. Some headlines about the wings. Basic geometry, 7 degrees dihedral, very slight washout, 16% thickness to chord at the root, 37.5% taper. Just under 21.5 meters span, which at an area of just under 42 square meters means an aspect ratio of about 11. Each wing holds 1,610 liters of jet fuel in an integral tank, which weighs about 10% of the MTOW, which is 13 tons or so. So the total fuel weight fraction is around 20%, which is around what you'd expect on a little regional turboprop. It's closer to 40% on a long-haul jet. So let's look at what all this means in terms of payload and range trade-offs. First of all, what we're looking at here is a very conservative range value. It assumes that after covering this distance in ISA conditions at 19,000 feet, we are maneuvering for 10 minutes, holding for 45 minutes at 5,000 feet, and then diverting to an alternate 100 nautical miles away. Now, up here, we have a corner trimmed off the max payload range polygon due to being limited by the structural load carrying capability of the aeroplane to about 3.9 tons of payload. This is essentially the maximum zero fuel weight of the aeroplane. So up to this first kink in the graph, we can put an 86 kilogram passenger in every one of the 34 seats. That makes about 3.9 tons. Of course, as we move up the range axis, we need to keep adding more and more fuel. And with the just over 1 ton needed here, we hit the maximum takeoff weight, so that takes over as the limiting factor, hence the kink. As we burn somewhere between 400 and 500 kilograms of fuel per hour, plus we have all those contingencies built in, at this point we have a nominal air range of 330 nautical miles or so. If we need more range, we need to start trading passengers for fuel. So, flying with 4 empty seats, those passengers' weight in fuel could take us quite a bit further, approaching 600 nautical miles. We could fly our 34-seat aeroplane with 25 passengers beyond 800 nautical miles with contingencies. And we can keep stretching the range by replacing passengers with fuel until we get to this kink point, defined by the aforementioned 1.3 ton per side fuel tank capacity limit. Now, at this point, we can carry on removing passengers, but the range will only increase slightly as we cannot add more fuel, but the induced drag and therefore the cruise power required and thus the fuel burn reduces a little by virtue of the aeroplane getting lighter. Now, as it turns out, in everyday airline service today, these trade-offs tend to be somewhat academic, with most operators only really using this chunk of the payload range space for passenger services. For example, Loganair in the UK used their Saabs in this lovely tartan livery for relatively short hops connecting Aberdeen and Glasgow with Orkney and Shetland. At these sorts of distances, the weight and thus passenger number is only limited if a remote destination doesn't have refueling facilities, so the calculation must cover the return trip. Or it could be limited by field performance constraints. Now, you might be wondering what the point of a 2.6 ton fuel capacity might be if typical passenger operations rarely need much more than a ton. Well, part of the answer is cargo. Freighter conversions of the 340 really benefit here, especially for comparatively low density cargo. In fact, this operator specifically advertises the cargo volume available, 36 cubic meters. If what you're transporting is perhaps relatively bulky, but doesn't weigh much more than 2.5 tons, then you can pretty much cross Europe with it, for example, or do a US transcon with 1 refueling stop. In fact, because cargo nets and tie downs and the window blanks you typically find on freighter conversions are generally lighter than the discarded passenger seats and windows and a galley, you can probably even count on a little bit of payload headroom beyond what you get on the passenger version, though once again, obviously only up to the limits set by the maximum zero fuel weight. So where does this place the Saab 340 amongst its competition? The year of its first flight saw 2 other regional turboprop twins make their maiden sorties, the slightly smaller 11.5-ton 30-seat Embraer Brasilia and the slightly larger 15.5-ton 37-seat Dash 8 Series 100. And here is a rough comparison of their payload range envelopes against the Saab 340B in blue. I say rough because they vary somewhat depending on the cruise speed, and the Dash and the Brasilia also have extended range variants that push the fuel limit lines on the right further out. In fact, the extended range tanks give the Dash a ferry range of more than double the numbers we see here. With the payload range slopes being quite similar here, in theory, a similarly extended range Saab 340 might be possible too,
provided that the necessary fuel tank volume is found. By the way, isn't it fascinating how the three design teams, working on three different continents but at about the same time, towards very similar design briefs, came up with three different layouts? The Embraer 120 has a low wing and a T-tail, sort of like a stretch version of Embraer's 1970s nine-seater, the 121 Xingu. This traces its lineage back to Embraer's earlier, smaller turboprop twin, the Bandeirante. However, that had a conventional tail. The DHC-8 had a T-tail, like the Brasilia, but a high wing and an engine nacelle-mounted main landing gear. Incidentally, the Dornier 328, which joined the fray of the 30-ish seat regional twin turboprops a decade later, also had a high wing, but a fuselage-mounted main landing gear. The slightly larger contemporary of the trio of 1983 turboprop twins, the ATR 42, seen here in its latest version, has the same layout, highlighting what is perhaps its main advantage, the proximity of the forward door to the tarmac. But I digress.
Perhaps the most important subject we teach our aeronautics and astronautics students at the University of Southampton is what one might call flight mechanics, covering a range of topics from the fundamentals of aircraft performance to dynamic stability. Now, 4,000 horsepower cherry on the top of the cake of these 2 semesters or so, wild mix of metaphors there, is a rather special Saab 340 flight provided to our students by Captain Rob Harrison and his crack team from the National Flying Laboratory Centre from Cranfield, with the subject of this video, their rather special B+, Golf, November Foxtrot Lima Bravo. On this flight, the students act as flight test engineers under the guidance of an experienced test engineer who is in the cabin with them, orchestrating a mini test campaign with the pilots and the the student task specialists who take measurements as Lima Bravo visits interesting parts of its flight envelope. These are maneuvers aircraft don't normally see in airline service. Instead, what we're getting here is a bit like a heavily abridged version of the Part 25 initial airworthiness certification testing of the type. Now, for all this to be quantifiable, we need to know a lot of numbers about the aeroplane at any given time, such as its exact position in space, its attitude in roll, pitch and yaw, and of course the all-important air data, total and static pressure, outside air temperature, total temperature, angle of attack, side slip angle. We also need data about the aeroplane itself, such as propeller speed and torque, turbine speeds, control surface deflections and control forces. And this is where Lima Bravo really shines compared to other B+. It is a very special B+, a B++ you might say. Instead of a forward galley or lavatory, it has an instrumentation rack holding a data acquisition unit, plus an inertial navigation system with integrated satellite-based real-time kinematic positioning. The actual sensing capability is richer too than on production aircraft. For example, Lima Bravo has a pair of side slip vanes. So let's join this group of Southampton students who, after 2 semesters of flight mechanics and a detailed briefing on today's flight, are ready for this unique opportunity to learn in practice about the Saab and more generally about flight mechanics and flight testing.
Aeronaut 02 Charlie, clearances to leave controlled airspace, not above 2,000 feet, VFR squawking 3667, and next frequency when advised, Solent 120.230.
Aeronaut 02 Charlie, start approved and read back correct.
Start approved, Aeronaut 02 Charlie.
2, 1, NG, fuel on,
Fuel on.
fuel flow.
Hold pressure. There was also an emergency exit door at the front right-hand side, plus 2 overwing emergency exits in row 6. You should check the location of your nearest exit, which could be behind you. That's our takeoff signal, so just check your seatbelts, thank you.
So the point of today's flight on board what is almost certainly the world's coolest classroom is to experience, explore and measure some key aspects of the performance and the handling of the Saab 340B+. But as we climb out of Southampton Airport, we have a few moments before we get to work to admire the port of Southampton, its cruise terminals and the busy shipping lanes of Southampton water leading out into the Solent. This is also a good time to note that the Saab 340B is actually a really nice place to sit, partly because of its generous windows, partly because of a very passenger-friendly pressurization schedule, which maintains the sub-sea level ground roll pre-pressurization up to about 8,000 feet pressure altitude, and the cabin altitude then rises approximately linearly, but so slowly that in a typical 18,000–19,000 foot cruise, the cabin altitude is still barely 2,500 feet. Makes it a nice environment to work in too, so let us do just that as we're approaching our initial task altitude here.
Perhaps the most interesting item on this test flight is the demonstration of the stall warning and stall prevention system on the Saab. The beauty of this, beyond the associated roller coaster thrills, is that there is a tremendous amount of complexity hidden beneath what is a relatively simple maneuver, both from an aerodynamics and from an airworthiness point of view. Let's begin with the aerodynamics. So, the NFLC team will fly the maneuver here in a clean configuration in which we expect a 1G stall speed of somewhere between 85 and 105 knots indicated airspeed, depending on the weight of the aeroplane shown on the horizontal axis here. Now this stalling speed is shown by the thick blue line. Now, we will not reach that speed, certainly not at 1G, on the test flight because the stick pusher system of the 340B Plus will kick in approximately 2 knots above it. That's the dashed line here. And there'll be a warning too, about 5 knots above. By the way, the warning and the pusher are angle of attack triggered, not speed triggered. Now, deploying flaps, as you'd expect, shifts all this to lower speeds. The 340B has flap settings of 7, 15, 20 and 35 degrees, and for each of these we can generate a similar stalling speed, 1G stalling speed curve, as well as a pusher activation curve. Now, because we have the weights and we have the speeds and we know the wing area, we can convert these curves into something that is a bit more interesting from an aerodynamics point of view, such as CLmax. So we end up with a CLmax curve for each flap setting. Better still, we could improve this chart by plotting these as a function of something to do with the speed, the flow speed, or the flow conditions in general, such as Reynolds number. So we end up with a picture that looks like this. And it's quite an interesting picture because normally, at least in back of the envelope calculations, you would expect the lift coefficient to be a feature of the geometry and therefore constant with flow conditions. Yet, here, clearly, each of these has a slight upward slope. Very interesting. I thought, at first I thought I'd made a mistake in making the conversion. So I went looking through NASA's library of technical reports and found this. A paper written by two scientists who took a wing section with the same aerofoil profiles as used by Saab on the 340B and took it to a wind tunnel and ran it through its through a wide range of Reynolds numbers from 2 till about 10 million, and came up with this CLmax chart. Now, of particular interest to us is the clean operating Reynolds number range of the Saab 340, which would be somewhere between 6 and 8 million or so. And quite interestingly, they seem to have found that exact trend we were looking at a moment ago. So, the CLmax of the 340 and the CLmax of the wing they tested there varies with Reynolds number. Let's look at the actual flight tests flown by the NFLC crew for us. If I go back to the picture of stalling speeds versus weights, I've put an arrow on here representing the weight of the aircraft at the time the flight test, at the time of the flight test you're about to see. So about 11.5 tons. And what you're about to see is the aircraft slowing down gradually, and we're approaching the clean pusher speed. First, we get a stall warning about 5 knots before the anticipated stall speed, and then you're going to see the stick push happen approximately 2 knots before the anticipated stall speed. First, some pre-test housekeeping, including advancing the condition lever to max, which increases the propeller speed from the cruise setting of 1,230 RPM to the max NP of 1,396 RPM. Listen to the change in the sound of the powertrain as Rob does that. The actual demonstration is based on the technique prescribed for establishing the stalling speed as part of the airworthiness certification process. Trim the aeroplane in steady level flight somewhere around 30% above the anticipated stall, with the power lever brought back to flight idle. Then use the elevator control to maintain a constant deceleration rate of about 1 knot per second indicated. First the oral stall warning and the shaker, about 5 knots above stall. Then the push, 2 knots above the minimum flying speed. So let's put all that cool instrumentation on board the National Flying Laboratory Centre's 340B+++ to good use here by dissecting a little bit the last few seconds and a few seconds after the stick push event we just witnessed. So we've got 2 reference points here in time. The horizontal axis showing time to maximum alpha. So the first grey line here shows the point where we recorded the maximum angle of attack during the maneuver, followed immediately by another grey line which shows the moment where the minimum speed was reached during the stick push event. So what have we here? We have the elevator deflection shown in blue, and you can see that the stick push event in terms of elevator deflection is not subtle. We have this huge spike going all the way up to the stick pusher elevator authority limit set to 7.5 degrees on the 340B. I say 340B specifically because it was 4 degrees on the 340A. So the authority of the stick pusher was increased relatively significantly for the next iteration of the design. The conversations about the authority of automatic pitch control systems goes back far deeper into history than just the 737 MAX that has been making the news of late. Now, we also see the normal acceleration, which we felt quite strongly in the on board the aircraft. Again, there is a big spike as we go down to about 0.2 G during the in the next few seconds following the stick push event. Now, there's another really interesting feature that I'd like to draw your attention to here, which is that we are at about 1 G 15 seconds before the event, but as we are approaching the stick push point and the aircraft is slowing down, we are descending slightly. We're beginning a descent, and that beginning of the descent is causing a reduction in the normal acceleration. And this is really important because this is a distinction between this sort of airworthiness testing type stick pusher test maneuver and the type of maneuver a student pilot would be flying, for example, preparing for a private pilot's license exam, where students are typically told to keep pulling back on the stick such that they maintain altitude in the run-up to the stall, and then you would expect a constant 1 G as you're approaching the stall event. We don't have a constant 1 G in this event, where the focus in this maneuver, this pusher test maneuver, where the focus is to reduce the speed gradually at a constant rate as we are approaching the stick pusher activation. Elevator control forces, as you would expect, they're increasing. Joe is pulling a good 5 kilograms there as we're approaching the push event, until the pusher takes the yoke out of his hand with a 15 kilogram or so kick. As I mentioned,
we're losing altitude in the run-up to the push event, and that's quite clear on this pressure altitude chart. And of course there is a significant loss of altitude once the pusher does its thing before the crew begin the gradual process of recovering straight and level flight. Angles, we reached a maximum alpha of approximately 14 degrees or so in the course of the maneuver, at which point the pusher kicked in. As I mentioned, it's an alpha activated event, not a speed activated event. Speaking of speed, here's the true airspeed in green and the indicated airspeed in blue. Now I mentioned that the goal, as prescribed in part 25, in fact, is to approach the store point, or the stick push point in this case, at a speed loss rate of 1 knots per second. And sure enough, 10 seconds before, we have approximately 10 knots above the stick push point. So some really precise flying there by Captain Joe Brown. If you want to better understand the airworthiness considerations behind the stall warning and protection systems on the Saab 340, you could start by looking up the certification basis of the aircraft. The original type certificate was issued by the Swedish Civil Aviation Authority, the LFV, on the basis of a document, the relevant paragraphs of which will have looked something like this 1989 excerpt from JAR 25. Also, if you'd like to know more broadly about the airworthiness aspects of store and store protection systems, I cannot recommend enough this volume by Guy Grattan, crystal clear and speaking from a position of authority on every page. It will also give you more of an insight into the differences between the aerodynamicist's concept of store and the airworthiness engineer's store. In the next half hour or so, the team from Cranfield proceeded to put the Saab through its paces. First up, an insight into the cruise performance of the aircraft through flying a series of straight and level measurement points at a range of speeds, with the students noting the fuel flow rates at each, as well as the estimated thrust of the aircraft derived from the propeller torque and the propeller performance curves. This then would allow us to draw up the drag polar of the aircraft, as well as to calculate its best range and best endurance speeds. There followed a series of static stability experiments, starting with longitudinal static stability. This involves once again flying a series of constant speed sections, this time measuring elevator and trim tab deflections in each case, the ultimate goal being determining the location of the neutral point. The ever-popular longitudinal maneuver stability tests were next, designed to determine the maneuver points and the all-important stick force per G. For this, a series of steady turns are flown at the same power setting and speed, but each at a higher elevator deflection and thus a steeper bank angle and greater load factor. Why do I say ever popular? Well, this is an extremely rare opportunity to experience 2G and a 60-degree bank angle in an airliner, along with the excitement of trying to take notes when your arm weighs twice as much as it did a few seconds earlier. Closing the static stability section of the laboratory session, steady heading side slips were on the menu as part of exploring the lateral directional stability of the aircraft. finally, a Swedish smorgasbord of maneuvers designed to give us some insights into the dynamic stability of the 340B, starting with a demonstration of the short period pitching oscillation. Simulating a pitch disturbance by giving a quick impulse to the elevator and watching the angle of attack return to its original value.
What you can feel as alpha increased, you've got additional lift force. It's actually behind the CG, so we get a nose down recovery. Drag. Also, as the speed's building up, you can feel the load factor.
Conversely, a constant angle of attack is a feature of the Phugoid oscillation, seen here in the next maneuver demonstrated by the team from Cranfield. The 340B oscillating at this airspeed at a period of about a minute, with the pitch angle and the airspeed changing, but alpha staying the same. At the crest of the wave, the speed can actually drop below the 1G stall speed, but we are nowhere near the stall alpha, and indeed we are below 1G at the top. And here is what the Saab's Phugoid looks like, speeded up 20 times. Now, I suggested earlier in this video that the two ventral fins under the aft fuselage may have something to do with improving the natural Dutch roll damping of the Saab. Let's see what this looks like, a rare opportunity to experience it in all its glory without the yaw damper. Then, let's see it with the yaw damper turned on.
Well, let's drive the motion now, left to right. With the motion now. So see, it does die away. It is stable, but it's poorly damped. So this time we're going to show you the yaw damper effect by repeating the input. This time we'll put the yaw damper in at the end. Driving the motion now. Here we go. Stopping now, yaw damper now. So you see there, that's the motion there of the yaw damper in the green there. It's served to counteract the yaw and has, in effect, cancel out that motion. That's what we want. We'd want that to be used the whole time.
And here are two screenshots from the Flying Classroom's in-flight entertainment tablets. At the bottom, the natural Dutch roll, convergent, perhaps courtesy of the fins, but it sort of goes on a bit in the area I drew that orange ellipse around, whereas with the damper on, it just stops dead. And you can see why at the very top of the picture where I captured Simon's red cursor, a fairly decisive rudder input there from the yaw damper. So there we are, at the end of our deep dive into some of the design ideas that shaped the Saab 340. I call this a design deep dive, but in truth we still barely scratched the surface of the thinking behind and evolution of this rather interesting, clever little turboprop from the 1980s. So many other interesting tales to tell about the 340, for example around airframe and engine inlet icing, some really interesting design airworthiness and operations issues and history there. Its field performance, its somewhat unusual flight control system architecture, and so on. Perhaps another time. For now, thank you for watching.